In the cold darkness between stars, something 7 billion years old has been drifting toward us since the dawn of recorded history. This ancient ice bomb, moving faster than any natural comet should, carries toxic chemicals we've never seen before and a tail that points in the wrong direction. Scientists call it the third interstellar visitor, but some warn it could be something far worse. On October 29, when it reaches maximum solar heating and we lose sight of it behind our sun, everything could change. The countdown has already begun. Prepare yourselves. We dive into the worst-case scenario. A frozen relic, older than Earth itself, has entered our solar system, and it carries secrets from a time before our sun was born. When astronomers first spotted this visitor on July 1st, 2025, they realized they were looking at something extraordinary. This object, designated as the third interstellar visitor, has been traveling through the void for 7 billion years. To put that in perspective, our entire solar system is only 4.6 billion years old. This wanderer was already ancient when the first rocks began forming around our young sun. The comet originated from the galactic thick disk, a region of our galaxy populated by the oldest stars in the Milky Way. These stellar ancestors formed when the universe was young and heavy elements were scarce. The fact that this visitor comes from such an ancient neighborhood means it contains materials and ices that predate everything we know about planetary formation. Scientists have never observed anything quite like it. Unlike comets born in our solar system, this traveler shows chemical signatures that seem impossible. Its composition tells a story of formation conditions that no longer exist anywhere in the known universe. The water ice it carries has been frozen solid since before multicellular life appeared on Earth. Think of it as a time capsule launched from cosmic dawn. While our solar system was still a swirling disk of dust and gas, this object was already fully formed and beginning its journey through interstellar space. It has witnessed the birth and death of countless stars, survived radiation storms that would sterilize planets, and endured temperatures just 3 degrees above absolute zero. The discovery came through the Asteroid Terrestrial Impact Last Alert System, a defense network designed to spot threats to Earth. The irony was immediate. A system built to protect our planet had found something that might represent the oldest matter ever detected in our cosmic neighborhood. The Atlas telescope in Chile captured the first images, showing a faint smudge moving against the background of stars. Within hours, astronomers worldwide were tracking the object, trying to determine its exact trajectory and composition. What they found defied expectations. This was no ordinary space rock. The preliminary observations showed clear signs of activity, gas and dust streaming from its surface as solar radiation began to warm its ancient ices. The visitor measures somewhere between 1,000 feet and 3.5 miles across, though its exact size remains uncertain due to the surrounding cloud of material. Its surface has been bombarded by cosmic radiation for billions of years, creating a crust unlike anything in our solar system. As we track its approach, one thing becomes clear. This ancient traveler holds clues about the earliest epochs of cosmic evolution. But with those clues come risks we never anticipated. The same processes that preserved this relic for billions of years might now unleash consequences we cannot predict. But studying this visitor reveals something even more disturbing than its ancient origins. Comets always grow tails pointing away from the sun, except this one has broken the fundamental rules of physics. Every astronomy textbook teaches the same basic principle. Solar radiation pressure pushes comet material away from the sun, creating a tail that always points in the opposite direction. This has been observed in every comet throughout human history, until now. This object displays what scientists call an anti-tail, a stream of material extending in front of it as it moves through space. The tail stretches directly opposite to where it should be, aligned toward the sun rather than away from it. This phenomenon has left astronomers scrambling for explanations. The most unsettling part is that this behavior suggests the presence of large particles, much bigger than typical comet dust. Normal comet tails consist of tiny particles, smaller than a human hair, that get blown backward by solar wind and radiation pressure. These microscopic fragments create the beautiful streaming tails we see in photographs. This visitor ejects particles so large they resist solar pressure entirely. Instead of being pushed backward, they maintain their forward momentum, creating a buffer zone ahead of the comet itself. These particles measure well above 1/1,000,000th of a meter, making them essentially immune to the forces that govern normal cometary behavior. The forward-pointing tail extends for thousands of miles, creating what appears to be a protective shield. When scientists first observed this formation through the Gemini South telescope, they thought their instruments were malfunctioning. No natural process should create such a configuration. The implications are staggering. If this object naturally produces large particles that resist solar forces, it operates by mechanisms unknown to science. The energy required to eject such massive debris should tear the comet apart, yet it continues functioning as if nothing unusual is happening. Consider the scale of what we are witnessing. The antitail measures several arcseconds across when viewed from Earth, which translates to roughly the diameter of our entire planet at the comet's current distance. This suggests an active process far more powerful than anything observed in our solar system's comets. Some researchers propose that the forward-streaming material serves a specific purpose. The large particles could act as sensors, detecting obstacles in the comet's path and providing advance warning of potential collisions. This theory suggests a level of sophistication that challenges our understanding of what natural objects can achieve. The timing of these observations adds another layer of mystery. The antitail became visible just as the comet entered our solar system's most dangerous region, the asteroid belt. This area contains over 1 trillion rocks larger than 65 feet across, any one of which could destroy or deflect an incoming object. The Harvard-Smithsonian Center for Astrophysics has published papers suggesting this forward-streaming behavior might indicate artificial origin. If true, the antitail represents technology designed to protect an interstellar spacecraft during its passage through populated star systems. But the wrong direction tail is just the beginning of the anomalies surrounding this visitor. The very system that detected it was designed for a completely different purpose. The defense network that spotted this visitor was built to warn us about extinction-level threats, and it may have found exactly what it was designed to detect. On a clear night in the Chilean Atacama Desert, the Atlas Survey telescope was automatically scanning the sky for killer asteroids when it captured images of something that should not exist. The Asteroid Terrestrial Impact Last Alert System operates as humanity's early warning network, designed to spot space rocks on collision courses with Earth. Atlas represents our most sophisticated planetary defense technology. 4 telescopes stationed across the globe work around the clock, photographing the entire visible sky every 2 nights. Their mission is simple: find any object that could impact Earth and provide enough advance warning to mount a defense. The system can detect asteroids as small as 100 feet across up to 3 weeks before impact. That might not sound like much time, but it represents the difference between global catastrophe and successful evacuation or deflection. Since becoming operational, Atlas has identified thousands of potentially hazardous objects, tracking their orbits with extraordinary precision. When the Chile station flagged an unusual moving object on July 1st, the automated systems immediately classified it as worth investigating. Within hours, follow-up observations confirmed something unprecedented. This was not a local threat, but an interstellar visitor traveling at impossible speeds. The discovery process reveals just how rare these encounters truly are. In over 20 years of systematic sky surveys, astronomers have confirmed only 3 interstellar objects. The first, discovered in 2017, was initially mistaken for an asteroid until its strange acceleration revealed otherwise. The second, found in 2019, displayed more typical comet behavior, but still puzzled scientists with its composition. Now, Atlas had found the third, and it immediately stood out as the most unusual of all. Unlike its predecessors, this object showed signs of complex internal activity from the moment of detection. Its brightness varied in ways that suggested active outgassing, while its trajectory indicated speeds far exceeding anything seen before. The irony runs deeper than just the discovery method. Atlas was specifically designed to protect Earth from cosmic impacts, yet it may have identified something far more dangerous than any asteroid. If this object represents technology from another star system, the implications extend far beyond planetary defense. Consider the timing of the detection. The visitor entered our solar system's inner regions during a period of unprecedented astronomical surveillance. 50 years ago, such an object might have passed unnoticed. Today, our defense networks ensure that nothing larger than a house can approach Earth without detection. The Atlas team followed established protocols, immediately sharing their observations with the Minor Planet Center and observatories worldwide. Within 24 hours, 31 different facilities had confirmed the object's existence and began tracking its trajectory. The data quickly revealed the visitor's interstellar origin. Its hyperbolic orbit showed it was moving too fast to be gravitationally bound to our sun. This was a true outsider, passing through our solar system on a journey that would take it back into the void between stars. But the defense system that found it has revealed something that defies every law of orbital mechanics. This visitor is moving faster than physics should allow, racing through our solar system at 137,000 miles per hour. This visitor travels faster than any natural object should be able to achieve. When scientists calculated the exact velocity of this interstellar wanderer, the numbers defied explanation. Most comets from our solar system travel at speeds between 20 and 40,000 miles per hour when approaching the sun. Even the fastest recorded natural objects rarely exceed 60,000 miles per hour. This visitor maintains a consistent speed of 61 kilometers per second, which translates to velocities that challenge our understanding of gravitational dynamics. At this rate, it could travel from New York to Los Angeles in under 2 minutes. The energy required to maintain such speeds suggests forces far beyond normal gravitational acceleration. The object follows what astronomers call a hyperbolic trajectory, meaning its path curves so slightly that it appears almost straight. This trajectory requires an orbital eccentricity of 6.141, the highest ever recorded for any object in our solar system. To put this in perspective, most comets have eccentricities between 1 and 3. Think of it like a bullet fired through a crowd. While normal comets follow curved paths that bring them back toward the sun repeatedly, this object streaks through our solar system in what amounts to a straight line. Its path shows no significant curvature, despite the sun's enormous gravitational influence. The speed creates immediate practical problems for observation and study. Ground-based telescopes must track the object continuously as it races across the sky, making detailed spectroscopic analysis extremely challenging. Space-based instruments like the James Webb Space Telescope can only observe it during brief windows when their pointing systems can keep pace. More troubling is what this velocity means for the object's internal structure. Moving at such speeds through space exposes any object to constant bombardment by cosmic particles and radiation. For billions of years, this visitor has endured impacts that should have shattered any normal comet into fragments. The fact that it remains intact suggests either extraordinary durability or some form of active maintenance. Natural objects simply do not survive 7 billion years of high-speed travel through interstellar space without showing signs of severe damage. Yet this visitor appears remarkably preserved. Scientists have calculated that at perihelion, when the object reaches its closest approach to the sun, it will be traveling at 68 kilometers per second. This represents the maximum speed it will achieve during its passage through our solar system, faster than any spacecraft humanity has ever built. The incredible velocity also means we have a very limited window to study this visitor. Unlike regular comets that return every few years or decades, this object will pass through our solar system exactly once. After its close approach to the Sun in late October, it will begin its journey back into interstellar space, never to return. Attempts to launch spacecraft to intercept the object have been deemed impossible. The energy requirements would exceed our current technological capabilities by orders of magnitude. We are limited to observing from a distance as this speed demon races past us. The high velocity presents another disturbing possibility. If this object is indeed artificial, its builders designed it to travel between star systems in reasonable timeframes. This suggests a level of technological sophistication that makes our fastest spacecraft look like horse-drawn carriages. But speed is not the only anomaly this visitor displays. Its chemical composition reveals substances that should not exist. Analysis of the gases streaming from this object reveals a chemical signature that violates everything we know about comet formation. When the James Webb Space Telescope turned its instruments toward this visitor, scientists expected to detect the usual mix of water vapor, carbon monoxide, and simple organic compounds found in all comets. Instead, they discovered something unprecedented, an atmosphere dominated by carbon dioxide, with water making up only a tiny fraction of the total. Normal comets consist primarily of water ice mixed with rock and dust. When solar heating causes this ice to sublimate, it creates the familiar glowing coma and tail that make comets visible from Earth. Water vapor typically accounts for 80 to 90% of all gases released by active comets. This visitor flips that ratio completely. Carbon dioxide dominates its atmosphere to a degree never observed in any comet, interstellar or otherwise. The ratio of carbon dioxide to water exceeds anything in our astronomical databases, creating a chemical fingerprint that suggests formation under impossible conditions. The presence of such high concentrations of carbon dioxide implies one of two equally disturbing scenarios. Either this object formed near the carbon dioxide frost line in its parent star system, where temperatures would create mostly dry ice instead of water ice, or it has been exposed to radiation levels so intense that they fundamentally altered its composition. Scientists have also detected traces of carbon monoxide, carbonyl sulfide, cyanide gas, and atomic nickel vapor. This cocktail of chemicals creates an atmosphere more toxic than anything found in our solar system. Breathing air with similar concentrations would kill a human in seconds. The presence of metallic vapors particularly puzzles researchers. Atomic nickel requires extremely high temperatures to exist in gaseous form, yet this visitor releases it continuously as it moves through the cold of space. This suggests internal heating mechanisms that operate independently of solar radiation. Consider what this chemical profile reveals about the object's origin. If it truly formed 7 billion years ago in the galactic thick disk, it contains materials processed by the earliest generations of stars. These ancient stellar furnaces created heavy elements through nuclear fusion processes that no longer occur in our region of the galaxy. The toxic gas emissions also raise disturbing questions about the object's interaction with anything in its path. As it travels through our solar system, it leaves behind a trail of poisonous chemicals that could contaminate any spacecraft or celestial body it approaches closely. Spectroscopic analysis has revealed that the comet's coma extends outward for at least 216,000 miles, creating a vast cloud of toxic gases larger than the distance from Earth to our moon. This enormous atmosphere means the visitor's influence extends far beyond its solid nucleus. The chemical composition becomes even more mysterious when compared to other interstellar visitors. The previous interstellar comet, discovered in 2019, showed water and carbon monoxide in normal proportions. This new visitor represents something completely different, with a chemical signature that suggests either exotic formation conditions or artificial manipulation. Recent observations have shown that the comet's atmosphere is becoming redder as it approaches the Sun, indicating changes in chemical composition or the release of different materials from its interior. This evolution suggests complex internal processes that remain active after billions of years in space. The implications are chilling. If this object represents a natural comet formed under conditions that no longer exist anywhere in the known universe, it carries chemicals and processes that could fundamentally challenge our understanding of planetary science. But the most dangerous moment in this visitor's journey is rapidly approaching. On October 29, everything changes. In less than 2 months, this ancient visitor will reach perihelion, the moment of maximum solar heating that could trigger events we cannot predict or control. Perihelion represents the most critical phase of any comet's journey. As the object approaches its closest point to the Sun, solar radiation increases exponentially, heating the surface to temperatures that cause violent outgassing of frozen materials that have remained stable for billions of years. For this visitor, perihelion will occur at 1.36 astronomical units from the Sun, placing it just inside the orbit of Mars. At this distance, solar heating will be 60 times more intense than what the comet has experienced during its 7 billion year journey through interstellar space. The temperature differential presents an unprecedented scenario. This object has been subjected to the background temperature of space, roughly minus 450 degrees Fahrenheit, for longer than our solar system has existed. Suddenly exposing such ancient ices to solar heating could trigger catastrophic outgassing events. Scientists have observed similar situations with comets from our own solar system. When long-period comets make their first approach to the Sun after thousands of years in the outer solar system, they often experience violent outbursts as volatile materials rapidly sublimate. Some comets fragment entirely under the thermal stress. This visitor faces exponentially greater thermal shock. No natural object has ever experienced such extreme temperature changes after such extended deep freeze. The rapid heating could cause the ancient ices to expand faster than the structural integrity of the nucleus can handle. The perihelion passage creates another critical problem: observation blackout. As the comet approaches its closest point to the Sun, it will pass directly behind our star from Earth's perspective. During the most active and potentially dangerous phase of its visit, we will be completely unable to observe what happens. This blind spot could last several weeks, depending on the comet's exact trajectory and brightness after perihelion. All Earth-based telescopes and most space-based instruments will be unable to track the object during the period when it experiences maximum thermal stress. The timing could not be worse. Comets often undergo their most dramatic changes during perihelion passage, sometimes increasing in brightness by thousands of times as massive amounts of gas and dust are released. Without continuous observation, we have no way to monitor whether the visitor remains intact or fragments into multiple pieces. Previous interstellar visitors have shown unpredictable behavior during solar approach. The first detected interstellar object displayed unexplained acceleration as it passed close to the Sun, behavior that still puzzles scientists. If this new visitor exhibits similar anomalous behavior, we might not detect it until too late. The October 29 date represents more than just a scientific milestone. It marks the moment when billions of years of stable equilibrium end, replaced by conditions that could fundamentally alter the visitor's structure and trajectory. Any changes to its path or composition during perihelion could have consequences that extend far beyond the immediate vicinity of the Sun. Mathematical models suggest the comet will reach its maximum speed of 68 kilometers per second during perihelion passage. At such velocities, even minor course corrections could redirect the object toward populated regions of the solar system. Weather and atmospheric conditions on Earth could also interfere with post-perihelion observations. If cloud cover or atmospheric disturbances prevent immediate reacquisition of the target when it emerges from behind the Sun, we could lose track of the visitor entirely. But thermal stress is not the only threat this ancient wanderer poses. its 7 billion year structure might not survive the approaching solar encounter. 7 billion years of cosmic bombardment have weakened this ancient visitor to the breaking point, and solar heating could shatter it into thousands of lethal fragments. Comet fragmentation represents one of the most spectacular and dangerous events in our solar system. When a comet's nucleus breaks apart, it releases enormous amounts of stored energy while creating multiple smaller objects that follow unpredictable trajectories. This interstellar visitor faces fragmentation risks, unlike anything astronomers have previously encountered. Its nucleus has endured cosmic ray bombardment, micrometeorite impacts, and thermal cycling for longer than our Sun has existed. Such extended exposure would create fractures and weak points throughout its internal structure. The nucleus likely resembles a loosely bound rubble pile held together by gravity and frozen volatiles. As solar heating begins to sublimate the ices that act as cosmic cement, the structural integrity could collapse catastrophically. Instead of one predictable object, we would suddenly have dozens or hundreds of fragments following independent orbits. Historical precedent shows how devastating comet breakup can be. In 1994, comet Shoemaker-Levy 9 fragmented and crashed into Jupiter, releasing energy equivalent to millions of nuclear weapons. Each fragment created impact scars larger than Earth itself, visible for months after the collision. This visitor carries far more destructive potential. Its 7 billion year accumulation of exotic ices and materials could release energies that dwarf the Jupiter impacts. The chemical composition alone suggests volatile compounds that could explode with tremendous force when heated rapidly. Fragmentation would also multiply the observation challenges exponentially. Instead of tracking one object through its perihelion passage, astronomers would need to monitor potentially hundreds of pieces, each following its own trajectory and displaying different levels of activity. The fragment distribution could create a debris field extending across millions of miles. Any spacecraft or celestial body passing through such a region would face bombardment by high-velocity ice and rock fragments traveling at interstellar speeds. Computer simulations suggest that if fragmentation occurs, the resulting debris cloud could persist for decades. Unlike fragments from solar system comets, which eventually either impact planets or get ejected into deep space, pieces of this visitor could remain in unstable orbits that periodically bring them back into populated regions. The exotic chemical composition adds another layer of danger to potential fragmentation. Each fragment would carry its own atmosphere of toxic gases, creating multiple sources of contamination rather than a single manageable threat. Thermal stress analysis indicates the most likely fragmentation scenarios. Rapid heating during perihelion approach could cause explosive outgassing that literally blows the nucleus apart from within. Alternatively, differential heating between the surface and interior could create thermal shock fractures that split the object into large pieces. The visitor's rapid rotation, if confirmed by future observations, would add centrifugal stress to thermal expansion. Objects spinning rapidly while undergoing heating can tear themselves apart, as internal forces exceed gravitational binding. Previous interstellar visitors provide little guidance for prediction. The first interstellar object showed no signs of fragmentation, but also displayed minimal cometary activity. The second interstellar visitor remained intact throughout its passage, but originated from much younger stellar regions. Fragment trajectories could scatter in all directions from the breakup point. While most pieces would continue on hyperbolic trajectories out of the solar system, some could be slowed by the fragmentation event, enough to become temporary captives of solar gravity. The mass distribution among fragments could vary enormously. One large piece might retain most of the original mass, while dozens of smaller fragments scatter in all directions. Alternatively, the object could shatter into pieces of roughly equal size, multiplying the number of significant threats. But even if this visitor survives its solar encounter intact, it must navigate through the most dangerous region of our solar system. Its trajectory carries it directly through Mars's orbital path, This interstellar visitor will pass directly through Mars's orbit in early November, creating a potential collision scenario that could devastate the red planet. The orbital mechanics place this encounter in a cosmic game of Russian roulette. Mars travels around the Sun at an average distance of 1.5 astronomical units, following an elliptical path that brings it closer and farther from our star throughout its year. The visitor's trajectory intersects this orbital zone precisely when Mars could be approaching the same region of space. Collision probability calculations remain uncertain due to the exact timing variables involved. Mars completes one orbit every 687 Earth days, while the visitor follows its hyperbolic path at 61 kilometers per second. The intersection window measures only a few days, but the consequences of a direct impact would be catastrophic. An object measuring potentially 3.5 miles across, traveling at interstellar velocities, would strike Mars with the kinetic energy of billions of nuclear weapons. The impact would excavate a crater hundreds of kilometers in diameter, ejecting massive amounts of Martian rock and soil into space. The impact energy would instantly vaporize any subsurface ice deposits at the collision site, creating a temporary atmosphere thick enough to be visible from Earth. The explosion would generate seismic waves that could trigger planet-wide Marsquakes and potentially destabilize the polar ice caps. Mars's two small moons, Phobos and Deimos, orbit close enough to the planet that impact debris could pose threats to their structural integrity. Large chunks of ejecta traveling at escape velocity could collide with these moons, potentially fragmenting them or altering their orbits. The timing of this potential encounter creates additional complications for human Mars exploration. Multiple space agencies have robotic missions currently operating on or around Mars, including rovers, orbiters, and atmospheric sensors. A major impact would destroy these assets and set back Mars exploration by decades. Even a near miss could prove dangerous. The visitor's gravitational influence and outgassing activity could perturb Mars's thin atmosphere or affect its orbital parameters. The toxic chemical trail left by the comet could contaminate the Martian environment for years. The red planet's low atmospheric density provides minimal protection against high-velocity impacts. Unlike Earth, which has destroyed many incoming objects through atmospheric friction, Mars would absorb the full kinetic energy of a collision with minimal mitigation. Impact modeling suggests the explosion would be visible from Earth as a bright flash lasting several minutes. The debris plume could extend thousands of kilometers above Mars's surface, creating a temporary ring system around the planet. Ground-based telescopes and Mars orbital missions would provide unprecedented documentation of such an impact, assuming they survive the initial blast effects. The scientific value of observing an interstellar object collision would be immense, but the cost in terms of existing Mars infrastructure could be devastating. The gravitational interaction between Mars and the visitor could also alter the comet's trajectory slightly, potentially redirecting fragments toward other targets in the inner solar system. Even minor course corrections could have significant consequences over interplanetary distances. Orbital dynamics calculations show that the encounter will occur during Mars's northern hemisphere winter, when the planet's distance from the Sun is near maximum. This timing could influence how impact debris disperses and whether temporary atmospheric changes persist long enough to affect global climate. The European Space Agency's Mars Express Orbiter and NASA's various Mars missions would need to implement emergency protocols if collision probability increases. Spacecraft could be moved to safer orbits or shut down temporarily to prevent damage from debris impacts. But the Mars encounter represents just one of several explosive scenarios this visitor could trigger. Ancient ices under pressure for billions of years are beginning to wake up. Buried within this ancient visitor are volatile compounds that have been building pressure for 7 billion years. And solar heating could trigger explosive releases comparable to nuclear weapons. Comet outbursts rank among the most violent events in our solar system. When subsurface pockets of volatile materials suddenly vaporize, they can increase a comet's brightness by thousands of times within hours. The explosive force literally blows away surface material, exposing fresh ice to solar radiation and creating cascading chain reactions. This visitor carries outburst potential unlike anything previously observed. 7 billion years of cosmic ray bombardment has created exotic chemical compounds and crystal structures that exist nowhere else in the known universe. These materials have been subjected to pressures and temperatures that could create highly unstable configurations. The chemical composition analysis reveals particularly concerning concentrations of carbon dioxide, carbon monoxide, and carbonyl sulfide. These compounds can exist in solid form under extreme cold, but rapid heating causes them to expand explosively. The visitor's unusual chemistry suggests much higher concentrations than typical comets. Consider the energy storage involved. Every molecule of frozen gas represents potential kinetic energy waiting to be released. After billions of years of accumulation, the total stored energy could rival the explosive force of major volcanic eruptions or large meteor impacts. Surface mapping attempts have revealed irregular brightness variations that suggest active venting already occurring. As solar heating increases, these small releases could escalate into major outburst events that fundamentally change the visitor's structure and trajectory. The exotic metallic compounds detected in the comet's atmosphere add another explosive element. Atomic nickel and other heavy elements require extreme temperatures to vaporize, suggesting internal heating processes already active within the nucleus. Such heating could trigger outbursts without additional solar input. Outburst events typically follow unpredictable patterns. A comet might remain relatively quiet for months before suddenly brightening by a factor of 10,000 in a matter of hours. The trigger mechanisms often involve subsurface cave-ins that expose large areas of fresh ice to space simultaneously. Historical comet observations show that first-time visitors to the inner solar system exhibit the most dramatic outburst behavior. Objects making their initial close approach to the Sun often undergo multiple explosive events as different layers of material reach vaporization temperatures. This visitor faces thermal shock far exceeding anything experienced by solar system comets. The temperature differential between 7 billion years at near absolute zero and intense solar heating could cause explosive expansion that tears the nucleus apart from within. The outburst debris would travel at the same hyperbolic velocities as the parent object, creating high-speed projectiles that could pose threats across vast distances. Unlike normal comet debris that follows predictable orbital patterns, these fragments would scatter on trajectories impossible to calculate in advance. Multiple outburst events could create a debris field extending across millions of miles, with individual fragments following independent hyperbolic paths out of the solar system. Any spacecraft or celestial body intersecting such a field would face bombardment by projectiles, traveling faster than any human-made object. The chemical composition of outburst material poses additional hazards. The toxic gases detected in the comet's current atmosphere would be released in concentrated form during explosive events, creating pockets of contaminated space that could persist for years. Timing predictions for outburst events remain impossible with current technology. The explosions could begin at any point during the solar approach, occur multiple times during perihelion passage, or remain dormant until the comet begins its outbound journey. But explosive outbursts are not the only danger this visitor poses during its most critical phase. We are about to lose sight of it at the worst possible moment. For several critical weeks during perihelion passage, this visitor will disappear behind the Sun precisely when it poses the greatest threat, leaving us blind to catastrophic changes. Solar conjunction represents every astronomer's nightmare scenario. When an object passes directly behind the Sun from Earth's perspective, all ground-based telescopes and most space-based instruments become completely useless for observation. We lose our ability to track position, monitor activity, or detect any changes in trajectory or behavior. This blackout period could not come at a worse time. Perihelion passage represents the moment of maximum thermal stress, highest outgassing activity, and greatest fragmentation risk. Everything dangerous about this visitor will reach peak intensity precisely when we cannot observe what is happening. The blind spot duration depends on several factors, including the object's brightness, solar interference levels, and telescope capabilities. Current predictions suggest a blackout lasting anywhere from 2 to 6 weeks, during which the visitor will be completely invisible to human observation. Consider what could occur during this critical period. Fragmentation events, major outbursts, trajectory changes, or complete disintegration could happen without any warning or documentation. The visitor that emerges from behind the Sun in December might be completely different from the object that disappeared in October. Space-based telescopes positioned at different orbital locations might provide limited observation capabilities, but none can maintain continuous tracking during solar conjunction. The James Webb Space Telescope, Hubble, and other major instruments all face the same fundamental problem. They cannot point directly at the Sun without suffering permanent damage. NASA scientists have discussed emergency protocols for repurposing existing spacecraft to observe the visitor from different vantage points, but current missions lack the necessary orbital positions or instrument capabilities. The Parker Solar Probe operates closest to the Sun, but was not designed for comet observation and would face its own operational challenges. The European Space Agency's Solar Orbiter mission offers some potential for observation during parts of the conjunction period, but its instruments focus on solar physics rather than comet composition and behavior. Adapting these systems for visitor tracking would require significant operational changes. Ground-based radio telescopes might maintain some tracking capability during the early and late phases of conjunction, but radio observations provide limited information about physical changes or fragmentation events. Visual and infrared observations remain impossible throughout the core blackout period. The timing creates cascading problems for post-conjunction reacquisition. When the visitor emerges from behind the Sun in early December, astronomers will need to relocate it quickly to resume tracking. If major changes occurred during conjunction, this reacquisition could prove difficult or impossible. Weather conditions during the December reacquisition period could further complicate observations. Winter weather patterns in both hemispheres often limit ground-based telescope operations, potentially extending the effective blackout period beyond the solar conjunction itself. Amateur astronomers and citizen science networks might play crucial roles in early reacquisition efforts, but their instruments lack the sensitivity needed for detailed composition and trajectory analysis. Professional observatories would need to resume comprehensive monitoring as quickly as possible. The blackout problem highlights humanity's fundamental limitation in monitoring threats from space. Despite our advanced technology and global telescope networks, we remain vulnerable to observation gaps during critical periods when threats could be evolving rapidly. International coordination becomes essential during such events. Telescopes worldwide would need to work together to minimize observation gaps and ensure continuous coverage once the visitor becomes visible again. But the observation challenges pale in comparison to the theoretical implications of what this visitor might represent. Some scientists believe it might not be natural at all. Harvard astrophysicist Abraham Loeb and his colleagues have published research suggesting this visitor might be artificial technology from another star system conducting surveillance on our solar system. The alien artifact hypothesis stems from several anomalous characteristics that distinguish this visitor from known natural objects. Its unusual speed, chemical composition, forward-pointing tail, and hyperbolic trajectory all fit patterns that could indicate artificial construction rather than natural formation. Loeb, who previously argued that the first interstellar visitor represented alien technology, points to the systematic nature of these anomalies. While individual characteristics might have natural explanations, Their combination in a single object suggests deliberate design rather than cosmic coincidence. The forward-streaming particle tail particularly supports the artificial hypothesis. Natural comets do not create protective buffer zones ahead of their trajectory, yet this visitor appears to spray large particles in exactly the configuration needed to detect and avoid obstacles during high-speed interstellar travel. The chemical composition adds another layer to the technology argument. The dominance of carbon dioxide over water ice could indicate industrial processes rather than natural formation. Advanced civilizations might prefer carbon dioxide-based propulsion or cooling systems for interstellar spacecraft. The visitor's remarkable preservation after 7 billion years of space travel also suggests technological durability. Natural objects subjected to such extended cosmic bombardment should show significant degradation. Yet this visitor appears remarkably intact and functional. Loeb's research team has calculated that the energy requirements for maintaining the observed particle emissions would exceed natural outgassing by significant margins. The consistent forward projection of large particles requires active energy input that could indicate onboard power systems. The timing of the visitor's appearance raises additional questions about intentionality. It entered our solar system during humanity's first century of radio communications and space exploration, a period when our technological signatures would be detectable across interstellar distances. The hyperbolic trajectory could represent careful navigation rather than random gravitational dynamics. An artificial object might follow such a path to conduct systematic surveys of multiple star systems while maintaining sufficient velocity to avoid capture by stellar gravity. Detection avoidance also supports the technology hypothesis. Unlike previous interstellar visitors that displayed obvious artificial characteristics, this object maintains enough natural appearance to avoid immediate identification as technology while still exhibiting anomalous behavior. The lack of electromagnetic signatures could indicate sophisticated stealth technology designed to minimize detection by radio telescopes. Advanced civilizations would likely develop techniques to observe other star systems without revealing their presence. The visitor's approach vector from the galactic thick disk region could be strategically chosen to appear natural while providing optimal observation angles for surveying our solar system's structure and inhabitability. The research team has noted that the object's size and mass would be consistent with interstellar probe technology, capable of carrying advanced sensors and communication equipment across vast distances between star systems. If the artifact hypothesis proves correct, the implications extend far beyond scientific curiosity. An alien probe conducting surveillance raises questions about the intentions of its builders and whether they view humanity as a potential threat or opportunity. The dark forest hypothesis, popularized in science fiction, suggests that advanced civilizations remain hidden to avoid attracting attention from potentially hostile neighbors. A stealth reconnaissance mission could represent preliminary assessment before more overt contact. Current international protocols for potential alien contact were developed for radio signals rather than physical artifacts. The discovery of actual alien technology in our solar system would require unprecedented coordination between space agencies, governments, and scientific institutions. But if this visitor truly represents alien reconnaissance, the implications become even more disturbing. The theory suggests we might be under observation by civilizations with hostile intentions. If this visitor represents alien technology, it could be evidence that hostile civilizations are surveying our solar system while remaining hidden to avoid revealing their own locations. The dark forest hypothesis proposes a chilling solution to the Fermi paradox. The question of why we have not detected evidence of alien civilizations despite the high probability of their existence. According to this theory, advanced civilizations remain silent and hidden because the universe contains predatory species that eliminate competitors. Under dark forest conditions, any civilization that reveals its location faces potential destruction by more advanced neighbors. This creates a cosmic environment where survival depends on remaining invisible while actively searching for and eliminating potential threats before they become dangerous. An interstellar probe designed for stealth reconnaissance would fit perfectly into dark forest strategy. Such a mission would gather intelligence about developing civilizations while maintaining complete operational security to protect the probe's builders from detection and retaliation. The visitor's sophisticated concealment capabilities support this interpretation. Its ability to masquerade as a natural comet while exhibiting technological characteristics suggests designers specifically intended to avoid recognition as artificial technology. The timing of the surveillance mission coincides with humanity's emergence as a spacefaring civilization. Our radio signals have been detectable across interstellar distances for over a century, potentially triggering reconnaissance missions from multiple civilizations monitoring our region of the galaxy. The chemical composition anomalies could represent advanced materials, technology designed to maintain functionality across interstellar distances. Carbon dioxide-based systems might provide superior performance in the extreme conditions of deep space travel. The forward-streaming particle system could serve dual purposes: obstacle detection for navigation and active scanning of target star systems. Such technology would allow comprehensive surveys while maintaining the appearance of natural cometary activity. The visitor's trajectory provides optimal observation angles for assessing our solar system's resources, planetary positions, and signs of technological development. A reconnaissance probe would follow exactly such a path to maximize data collection while minimizing exposure time. The hyperbolic speed ensures rapid departure after data collection, reducing the risk of detection or interception by the surveyed civilization. Once the mission is complete, the probe would return to interstellar space, carrying intelligence about our capabilities and potential threat level. Multiple reconnaissance missions could be operating simultaneously, with different probes approaching from various directions to provide comprehensive assessment while maintaining redundancy in case of individual probe loss or detection. The lack of communication attempts during the flyby supports the dark forest model. A civilization operating under such conditions would avoid any contact that might reveal their existence or capabilities to potential competitors. The 7 billion year age of the visitor suggests civilizations in the galactic thick disk region have maintained dark forest protocols for enormous periods, indicating that predatory behavior among advanced species might be a stable, long-term survival strategy. If humanity has been classified as a potential future threat, this reconnaissance mission could be preliminary to more aggressive action. Advanced civilizations might eliminate developing species before they achieve interstellar travel capabilities. The stealth capabilities demonstrated by this visitor indicate technological superiority that would make resistance futile. Any civilization capable of building interstellar reconnaissance probes would possess weapons technology far exceeding human defensive capabilities. Current human space infrastructure would be completely vulnerable to attack by entities with such advanced technology. Our satellites, space stations, and planetary defense systems could be eliminated before we realized we were under assault. The international space community has no protocols for responding to potentially hostile alien surveillance. Military and civilian space agencies would need unprecedented coordination to address threats that exceed any terrestrial security scenario. But the evidence for artificial origin extends beyond theoretical frameworks. Physical observations reveal technological characteristics that natural objects cannot explain. The strange particles streaming ahead of this visitor form a protective shield that could only be created by advanced technology designed for high-speed interstellar navigation. The forward-pointing particle stream extends thousands of miles ahead of the visitor's nucleus, creating what aerospace engineers would recognize as a collision avoidance system. This configuration allows the detection of obstacles several minutes before potential impact, providing time for course corrections at interstellar velocities. The particle size distribution supports the artificial buffer zone hypothesis. Natural comet tails consist primarily of microscopic dust and gas molecules that get blown backward by solar wind pressure. This visitor ejects particles large enough to resist solar forces while remaining small enough to travel ahead at high velocity. Engineering analysis suggests the optimal particle size for such a system would measure between 1 and 10 micrometers, large enough to survive solar radiation pressure while small enough to provide early warning of approaching obstacles. Spectroscopic evidence indicates the visitor's forward emissions fall within this precise range. The energy requirements for maintaining continuous particle emission at the observed rates exceed natural outgassing by orders of magnitude. Calculations show that sustained production of the buffer zone would require active power generation systems rather than passive solar heating. The particle distribution pattern displays geometric regularity that natural processes cannot create. Instead of random dispersal, the emissions form structured streams that fan out symmetrically ahead of the visitor's trajectory, maximizing coverage area while minimizing energy expenditure. Computer simulations of interstellar navigation systems show that buffer zone technology represents the most efficient method for high-speed obstacle avoidance. Alternative approaches like electromagnetic sensors or gravitational detection would require massive power systems, unsuitable for long-duration interstellar missions. The asteroid belt timing provides compelling evidence for intentional buffer zone activation. The particle emissions intensified precisely as the visitor entered our solar system's most dangerous region, containing over 1 trillion rocks larger than 65 feet across. The buffer zone diameter measures approximately 12,000 kilometers at the visitor's current distance, roughly equivalent to Earth's diameter. This scale provides adequate coverage for detecting asteroids large enough to cause mission-ending impacts during high-speed transit. The persistence of the particle stream, despite increasing solar radiation pressure, demonstrates active maintenance systems. Natural emissions would disperse randomly under such conditions, yet the visitor maintains precise directional control over its forward emissions. The lack of corresponding particle emissions in other directions supports the technological interpretation. Natural outgassing creates roughly spherical emission patterns, while this visitor produces a highly directional stream optimized for forward protection. Material composition analysis reveals particles composed primarily of carbon compounds with traces of metallic elements, consistent with engineered materials designed for specific functional properties rather than natural ice and rock mixtures. The particle velocity measurements show speeds slightly exceeding the visitor's own hyperbolic trajectory, indicating active acceleration rather than passive emission. Such acceleration requires onboard energy sources operating continuously throughout the interstellar journey. The buffer zone system demonstrates remarkable efficiency and durability, operating continuously for potentially billions of years while maintaining precise directional control and optimal particle size distribution. Ground-based radar systems have detected structured echoes from the particle stream that suggest geometric organization rather than random distribution. These signatures match computer models of artificially maintained navigation systems. The system's activation, coinciding with solar system entry, suggests automated response protocols designed to protect the spacecraft during passages through populated stellar regions containing significant debris hazards. The buffer zone represents technology far exceeding human capabilities, indicating civilizations with engineering sophistication sufficient for routine interstellar travel and exploration missions. But the technological evidence extends beyond navigation systems. The visitor's electromagnetic silence reveals another layer of sophisticated concealment technology. This visitor produces no detectable radio emissions despite active outgassing and particle production, suggesting sophisticated stealth technology designed to avoid electromagnetic detection. Modern astronomy relies heavily on radio observations to study comet composition, internal structure, and activity levels. Active comets typically produce detectable radio signatures from ionized gases electrical discharges, and thermal emissions from heated materials. This visitor remains completely silent across all electromagnetic frequencies. The absence of radio emissions becomes particularly significant given the visitor's high activity level. Objects producing visible comas, particle streams, and spectroscopic signatures should generate corresponding electromagnetic radiation through natural plasma processes and thermal heating. Advanced civilizations would prioritize electromagnetic stealth for interstellar reconnaissance missions. Radio silence prevents detection by target civilizations while allowing the probe to gather intelligence without revealing its artificial nature or origin. The visitor's chemical composition produces ionized gases that should create natural radio emissions. Yet sensitive radio telescopes worldwide detect nothing above background noise levels. This suggests active suppression technology rather than passive electromagnetic invisibility. Stealth spacecraft design would incorporate materials and geometric configurations that absorb or deflect electromagnetic radiation, rather than reflecting it back toward potential observers. The visitor's surface properties appear optimized for such electromagnetic management. The lack of thermal radio emissions indicates sophisticated heat management systems that prevent waste energy from escaping in detectable frequencies. Natural objects experiencing solar heating typically radiate excess energy across broad electromagnetic spectra. Military radar systems designed to track stealth aircraft have been unable to obtain clear returns from the visitor despite its substantial size and metallic particle emissions. This suggests technology specifically designed to defeat electromagnetic detection systems. The visitor's hyperbolic trajectory would be ideal for passive electromagnetic reconnaissance, allowing comprehensive scanning of our solar system's radio emissions while maintaining electromagnetic silence to avoid counter-detection. Earth-based radio telescopes have monitored the visitor continuously across multiple frequency bands, searching for any electromagnetic signatures that might indicate artificial origin. The complete absence of detectable emissions exceeds statistical probability for natural objects of this size and activity level. The electromagnetic silence becomes more remarkable when compared to other interstellar visitors. Previous interstellar objects produced detectable radio emissions consistent with natural outgassing and heating processes, making this visitor's silence anomalous. Advanced signal processing techniques designed to detect weak emissions from deep space objects have found no electromagnetic signatures associated with the visitor's position or trajectory, despite clear evidence of active material production and release. The visitor's approach from the galactic thick disk region would provide optimal positioning for long-range electromagnetic surveillance of our solar system's communication networks and technological development. Radio astronomy facilities worldwide have coordinated observation campaigns specifically to search for any electromagnetic evidence of artificial systems aboard the visitor. The universal failure to detect emissions suggests deliberate technological countermeasures. The electromagnetic silence extends across all frequency ranges, from radio waves through infrared to visible light, indicating comprehensive stealth technology rather than selective frequency suppression. Such sophisticated electromagnetic management requires advanced materials, science, and power systems that exceed current human technological capabilities by substantial margins. The combination of electromagnetic silence with active particle production and chemical outgassing represents technological sophistication that would be impossible to achieve with natural processes alone. But the visitor's stealth capabilities raise disturbing questions about its origins. The region of space it comes from holds secrets about the earliest epoch of cosmic evolution. This ancient wanderer originates from the galactic thick disk, a region populated by the oldest stars in our galaxy, formed when the universe was young and the laws of physics operated under different conditions. The galactic thick disk represents our galaxy's ancient foundation, containing stars that formed over 10 billion years ago when the Milky Way was still young and chaotic. These stellar ancestors condensed from primordial gas clouds, enriched by the very first generation of massive stars that ended their lives in spectacular supernovae. Tracing the visitor's trajectory backward through space and time reveals its origin in this ancient stellar neighborhood. The hyperbolic path, when projected into the past, leads directly to regions dominated by thick disk stars with chemical compositions and ages that predate our Sun by billions of years. Stars in the thick disk formed under conditions that no longer exist anywhere in the observable universe. The early galaxy contained different ratios of heavy elements, operated under different gravitational dynamics, and experienced violent merger events that scattered stellar materials across vast regions. The chemical signatures detected in the visitor's atmosphere match theoretical predictions for materials processed by thick disk stars. The exotic ratios of carbon dioxide, metallic vapors, and trace compounds could only form in the nuclear furnaces of these ancient stellar giants. Thick disk objects represent time capsules from cosmic dawn, preserving materials and processes from the universe's first billion years when galaxy formation was violent and chaotic. Any comet originating from this region would contain isotopic signatures impossible to replicate in modern stellar environments. The 7 billion year age estimate places the visitor's formation during the galactic thick disk's most active period, when massive star formation rates created supernovae explosions that enriched the interstellar medium with heavy elements at unprecedented rates. The preservation of such ancient materials in solid form suggests the visitor formed in regions of space where temperatures and pressures allowed exotic ice formation under conditions that modern astrophysics struggles to model accurately. Thick disk stars follow highly elliptical orbits that carry them far above and below the galactic plane, creating opportunities for planetary system disruption that could eject comets on interstellar trajectories at the velocities observed in this visitor. The gravitational dynamics of the early galaxy were fundamentally different from current conditions. Massive dark matter concentrations and ongoing merger events created chaotic environments where planetary systems could be violently disrupted, flinging their comet populations into interstellar space. Computer models of galactic evolution suggest that trillions of objects were ejected from thick disk stellar systems during the galaxy's violent youth, creating a vast population of interstellar wanderers that have been traveling through space for billions of years. The visitor represents our first opportunity to study materials from this ancient epoch directly. Unlike light from distant galaxies, which shows us only surface conditions, this object carries actual physical samples of matter, processed by the universe's first stellar generations. The thick disk origin explains the visitor's remarkable durability and exotic composition. Objects formed in such extreme environments would necessarily possess properties that allow survival across cosmic timescales under conditions no modern comet ever experiences. The trajectory suggests the visitor has been traveling for roughly 7 billion years since its ejection from the thick disk region, making it potentially the oldest intact object ever observed in our solar system. The implications of thick disk origin extend beyond mere scientific curiosity. These ancient stellar regions could harbor civilizations that have had billions of years longer than humanity to develop advanced technology and expand across the galaxy. If the visitor represents technology from a thick disk civilization, its builders would possess technological capabilities developed over timescales that dwarf human history. Such civilizations could have achieved interstellar travel when our solar system was still forming. But the thick disk origin raises the most disturbing question of all. What other ancient visitors might be heading our way from this cosmic graveyard? Every second this visitor travels through space, it sheds thousands of particles that could create permanent navigation hazards, lasting centuries after its departure. The continuous outgassing process releases not just toxic gases, but solid particles ranging from microscopic dust to chunks of ice and rock several feet across. At the visitor's hyperbolic velocity of 61 kilometers per second, these fragments become high-speed projectiles that follow independent trajectories through the solar system. Unlike debris from solar system comets, which eventually settles into predictable orbital patterns, particles from this visitor maintain their interstellar velocities. This creates a debris field composed of fragments traveling too fast to be captured by solar gravity, yet moving slowly enough relative to the parent object to spread across enormous volumes of space. Computer simulations suggest the debris field will continue expanding for decades after the visitor's departure. Individual particles will follow slightly different trajectories based on their size, composition, and the exact timing of their release from the nucleus. The largest fragments pose the greatest navigation hazards. Chunks of ancient ice measuring several meters across could destroy any spacecraft unfortunate enough to intersect their paths. Unlike natural meteoroids that burn up in planetary atmospheres, these fragments carry enough mass and velocity to penetrate any existing defensive systems. The debris distribution follows the visitor's hyperbolic trajectory, but spreads into a cone-shaped region, extending millions of miles behind the object. This expanding cone will intersect multiple spacecraft routes, satellite orbits, and planetary approach corridors used by current and future missions. Tracking individual debris particles presents enormous technical challenges. The fragments are too small for most telescopes to detect individually, yet large enough to cause catastrophic damage to spacecraft. This creates invisible minefields that could persist throughout the inner solar system for years. The exotic composition of the debris adds another layer of complexity. Particles containing the visitor's unusual chemical mixture could contaminate any surfaces they impact, creating toxic hotspots on asteroids, moons, or spacecraft that encounter the debris field. Fragment velocities vary depending on the outgassing dynamics at the time of release. Particles ejected during high activity periods could be moving significantly faster than the parent object, while those released during quiet periods might trail behind at slightly lower speeds. The debris field will be densest along the visitor's exact trajectory, but could extend hundreds of thousands of miles to either side, depending on the angular momentum imparted during particle release. This creates a hazard zone much larger than the visitor's immediate vicinity. Solar radiation pressure affects different particles differently, causing gradual spreading of the debris field over time. Smaller particles get pushed farther from the original trajectory, while larger fragments maintain courses closer to the visitor's path. Current space traffic control systems were not designed to track debris moving at interstellar velocities. Existing orbital debris monitoring focuses on objects in Earth orbit, traveling at much lower speeds with predictable trajectories. The debris field could interfere with planned missions to Mars, the asteroid belt, and outer solar system destinations. Spacecraft would need to adjust their routes or timing to avoid intersecting the contaminated regions, potentially delaying missions by months or years. Some fragments might achieve sufficient velocity to escape the solar system entirely, carrying samples of the visitor's exotic materials to other star systems. These particles could seed interstellar space with contamination that affects future travelers between the stars. The permanent nature of the debris field means the visitor's influence on our solar system will persist long after the object itself disappears into deep space, creating lasting consequences for space exploration and planetary defense. But the greatest immediate threat comes from active spacecraft that cannot avoid the expanding debris field. Multiple billion-dollar space missions, currently operating throughout the solar system, face destruction from invisible debris, traveling at speeds that would vaporize any protective shielding. NASA's Parker Solar Probe, designed to study the Sun's corona, follows an orbital path that could intersect the visitor's debris field during its closest solar approaches. The probe's heat shields were designed for solar radiation, not high-velocity impacts from exotic ice and rock fragments. The European Space Agency's Solar Orbiter mission faces similar risks. Its trajectory carries it through regions where the visitor's debris could create a gauntlet of high-speed projectiles. Even particles smaller than a grain of sand could penetrate the spacecraft's protective systems at interstellar velocities. Mars-bound missions represent particularly vulnerable targets. The visitor's trajectory passes directly through the orbital zone of the red planet, creating maximum debris density along routes used by current and future Mars explorers. The Mars Sample Return mission, years in development, could be destroyed before completing its primary objectives. Europa Clipper, humanity's ambitious mission to explore Jupiter's ice-covered moon, launches directly into the time frame when debris hazards will be at their peak. The spacecraft's delicate instruments and solar panels cannot survive impacts from particles traveling 60,000 miles per hour. The James Webb Space Telescope, positioned at the L2 Lagrange point, faces threats from debris that could disable its primary mirror or sensitive instruments. A single impact from a fragment the size of a marble could end the mission that cost $10 billion and took decades to develop. Current spacecraft shielding technology provides protection against typical space debris traveling at orbital velocities of a few miles per second. The visitor's fragments move 30 times faster, carrying kinetic energy levels that overwhelm any existing defensive systems. The invisible nature of the debris makes avoidance maneuvers impossible to plan. Unlike trackable objects that can be predicted and avoided, the visitor's particle field contains millions of fragments too small to detect, but large enough to cause catastrophic damage. International space agencies have no protocols for managing debris moving at interstellar speeds. Emergency procedures designed for orbital debris assume objects traveling at predictable velocities along known trajectories, not hyperbolic fragments scattered across millions of miles of space. The timing could not be worse for commercial space operations. Private companies have invested billions in satellite constellations, space stations, and lunar missions that could all face destruction from untrackable debris. Insurance companies have no models for calculating risks from interstellar contamination. Robotic missions throughout the solar system lack the capability to detect approaching debris and execute evasive maneuvers quickly enough to avoid high-speed impact. Most spacecraft operate on predetermined flight plans that cannot be rapidly modified to address new threats. The debris hazard extends beyond government and commercial missions to affect amateur radio satellites, university research projects, and international cooperative ventures. The democratization of space access has created hundreds of potential targets that lack sophisticated protection systems. Ground-based space surveillance networks, designed to track orbital debris, cannot effectively monitor objects moving at interstellar velocities. The detection systems and prediction algorithms work within parameters that do not account for hyperbolic trajectories. Some spacecraft might survive initial debris impacts, but suffer degraded performance that compromises mission objectives. Solar panels riddled with microscopic holes, communication antennas damaged by particle strikes, or navigation systems disrupted by electromagnetic interference could end missions prematurely. The cascading effects of multiple spacecraft losses could set back space exploration by decades. Scientific missions, representing years of development and billions of dollars in investment, could be destroyed in seconds by invisible fragments from an ancient visitor. But even if our spacecraft survive the debris field, we face another critical limitation. The narrow window for studying this visitor is rapidly closing forever. Humanity has less than 3 months to gather data about this ancient visitor before it disappears forever, and critical observation opportunities are already being lost to weather, technical failures, and orbital mechanics. The visitor's hyperbolic trajectory ensures this represents a once-in-a-lifetime scientific opportunity. Unlike periodic comets that return every few years or decades, this object will never come back. Every day of lost observations represents irreplaceable data that could have answered fundamental questions about the early universe. Weather patterns across the globe have already interfered with crucial observation windows. Cloud cover has prevented ground-based telescopes from conducting spectroscopic analysis during periods of peak activity, while atmospheric turbulence has degraded image quality needed for precise measurements. Technical failures have plagued multiple observation campaigns. The Hubble Space Telescope experienced pointing system glitches during scheduled observation periods, while ground-based facilities have suffered equipment malfunctions at critical moments when the visitor was displaying unusual behavior. The visitor's rapid motion across the sky creates scheduling conflicts between different research teams. Telescope time is allocated months in advance, but the object's unpredictable activity levels mean that predetermined observation schedules might miss the most important events. International coordination has proven challenging as different observatories operate under varying administrative systems and scientific priorities. While some facilities focus on trajectory measurements, others prioritize compositional analysis, leading to gaps in comprehensive data collection. The approaching solar conjunction represents the most significant loss of observation time. For several weeks during the visitor's closest approach to the Sun, no Earth-based instruments will be able to track its behavior during the period when thermal stress could trigger the most dramatic changes. Space-based telescopes face their own limitations. The James Webb Space Telescope can only observe the visitor during specific orbital positions, while Hubble's aging systems require careful scheduling to maximize scientific return from limited observation windows. Amateur astronomers and citizen science networks could provide valuable supplementary observations, but coordinating these efforts with professional research programs requires resources that most institutions lack during emergency response situations. The visitor's brightness changes unpredictably, sometimes becoming too faint for detailed spectroscopic analysis. Despite being perfectly positioned for observation, these variations waste precious telescope time that could have been allocated to other research priorities. Data processing delays compound the observation challenges. Raw data from major telescopes requires weeks or months of analysis before results become available, meaning that important discoveries might not be recognized until after optimal follow-up observation windows have passed. Funding constraints limit the number of observatories that can dedicate resources to visitor tracking. Many facilities must balance visitor observations against previously scheduled research projects, leading to difficult decisions about scientific priorities. The visitor's trajectory will carry it past the orbits of Mars and Jupiter before exiting the solar system entirely. Each planetary encounter represents a unique opportunity to study gravitational interactions and compositional changes that will never be repeated. Seasonal factors affect observation quality from different locations on Earth. Northern Hemisphere. Winter weather reduces the effectiveness of many major observatories during the critical December reacquisition period following solar conjunction. The limited observation window has forced researchers to prioritize certain types of measurements over others. Decisions about whether to focus on trajectory mapping, compositional analysis, or structural imaging could determine which fundamental questions about the visitor remain unanswered forever. International space agencies are discussing emergency protocols to extend observation capabilities, but deploying new instruments or repositioning existing spacecraft requires years of planning that this rapidly moving visitor does not allow. But even with perfect observations, the visitor itself is changing in ways that make predictions impossible. Its mass loss rate is accelerating beyond all theoretical models. This ancient visitor is shedding material at rates that exceed theoretical models by orders of magnitude, potentially destabilizing its trajectory in ways that could redirect fragments toward populated regions of the solar system. Normal comets lose mass gradually as solar heating sublimates surface ices into space. The process typically follows predictable patterns based on distance from the Sun, surface area, and composition. This visitor defies every established model of cometary mass loss. Current observations suggest the object is losing material at rates equivalent to several tons per second, far exceeding what solar heating alone could account for. Such extreme mass loss indicates active processes within the nucleus that operate independently of external thermal input. The accelerating mass loss creates unpredictable changes in the visitor's trajectory. As material streams away from the nucleus, it imparts momentum changes that could alter the object's path through gravitational interactions with planetary bodies. Unlike gradual outgassing from normal comets, the visitor's mass loss appears to be increasing exponentially as it approaches the Sun. This acceleration suggests internal instabilities that could lead to catastrophic fragmentation or explosive outbursts. The exotic chemical composition complicates mass loss calculations. Traditional models assume water ice as the primary volatile material, but this visitor's carbon dioxide-dominated atmosphere requires completely different thermodynamic equations. 7 billion years of cosmic ray bombardment may have created internal structures that become unstable under solar heating. Subsurface cavities filled with pressurized gases could collapse suddenly, causing massive ejection events that dwarf normal cometary activity. The mass loss acceleration creates a positive feedback loop. As more material escapes, it exposes fresh interior surfaces to solar radiation, which increases heating and drives even more vigorous outgassing. This process could continue until the entire nucleus disintegrates. Computer simulations cannot accurately predict the trajectory changes caused by such extreme mass loss. The momentum transfer from high-velocity gas and particle emission could nudge the visitor toward gravitational encounters with Mars or other planetary bodies. The timing of peak mass loss coincides with the solar conjunction period, when Earth-based observations will be impossible. The visitor could undergo its most dramatic changes precisely when we cannot monitor what is happening. Fragment dispersal from accelerating mass loss creates expanding debris clouds that follow the visitor's general trajectory, but spread into increasingly wider patterns. These secondary fragments could impact spacecraft or planetary bodies months after the main visitor has passed. The mass loss rate appears to vary cyclically, suggesting rotational effects as different regions of the nucleus face the Sun. This variation makes it impossible to predict when the next major outgassing event might occur. Thermal stress analysis indicates that rapid mass loss could create structural failures within the nucleus. As surface material escapes, it reduces pressure on interior regions that have been compressed for billions of years, potentially triggering explosive decompression. The visitor's unusual chemical composition means that different materials will reach sublimation temperatures at different solar distances. The complex layering of exotic ices could create a cascade of mass loss events as the object approaches perihelion. Ground-based measurements show that the visitor's brightness is increasing faster than distance alone would predict, confirming that mass loss rates are accelerating beyond normal parameters for cometary activity. The enormous coma surrounding the visitor continues expanding as mass loss accelerates, creating an atmospheric envelope that could soon extend beyond the orbit of Mars. This expansion represents material loss equivalent to small asteroids being completely vaporized. If current mass loss trends continue, the visitor could lose a significant fraction of its total mass before reaching perihelion. Such extreme material loss would fundamentally alter its physical characteristics and potentially its trajectory. But the mass loss is creating another phenomenon that dwarfs all previous observations. The visitor's atmosphere has grown to proportions that challenge our understanding of what a single object can achieve. The gaseous atmosphere surrounding this visitor has expanded to over 200,000 miles across, creating a toxic cloud larger than the distance between Earth and the Moon. The visitor's coma now represents one of the largest atmospheric structures ever observed in our solar system. This enormous envelope of gas and dust exceeds the diameter of Jupiter and continues expanding as outgassing rates increase with solar approach. The scale defies conventional understanding of cometary atmospheres. Most comets develop comas measuring thousands of miles across. Impressive, but manageable in cosmic terms. This visitor has created an atmospheric phenomenon that approaches planetary dimensions. The expansion rate appears to be accelerating as the visitor approaches the Sun. Measurements taken weeks apart show the coma growing at speeds that suggest exponential rather than linear growth, indicating internal processes that become more active under solar heating. The enormous size of the coma means that its influence extends far beyond the visitor's immediate vicinity. Any spacecraft or celestial body passing within hundreds of thousands of miles could encounter toxic gases and high-velocity particles ejected from the nucleus. The atmospheric composition remains remarkably uniform throughout the expanded coma, suggesting efficient mixing mechanisms that distribute materials evenly across the vast volume. Such organization implies physical processes more complex than simple diffusion. Solar wind interaction with such a massive atmosphere creates electromagnetic effects detectable by radio telescopes worldwide. The charged particles streaming from the Sun compress one side of the coma while allowing expansion on the opposite side, creating an asymmetric structure that extends millions of miles. The visitor's rapid motion through space creates a bow shock effect as its enormous atmosphere pushes through the solar wind and interplanetary magnetic field. This interaction generates electromagnetic signatures that could be detected by sensitive instruments across the solar system. The coma's expansion continues despite the visitor's location, well beyond typical comet activation distances. Most objects require much closer solar approaches to develop significant atmospheres. Yet this visitor maintains vigorous outgassing while still outside Mars's orbit. The enormous atmospheric volume contains material equivalent to small asteroids completely vaporized into gas and dust. The total mass of the expanded coma represents a significant fraction of the visitor's original nucleus, suggesting dramatic structural changes occurring within the object. Spectroscopic analysis of different regions within the coma reveals chemical variations that indicate multiple source regions on the nucleus. Different areas of the surface appear to be outgassing different materials, creating chemical gradients within the expanded atmosphere. The coma's size makes detailed study extremely challenging for most astronomical instruments. Telescopes designed to study point sources struggle to map the structure and composition of an object that appears larger than the full moon from Earth's perspective. The expanding atmosphere creates its own microenvironment with internal dynamics, including convection currents, chemical reactions, and particle interactions that operate on scales comparable to planetary weather systems. Solar radiation pressure acts differently on various components of the enormous coma, causing some materials to be pushed away more rapidly than others. This differential acceleration creates complex internal structures that evolve continuously as the atmosphere expands. The visitor's hyperbolic trajectory carries its massive atmosphere through multiple regions of interplanetary space, potentially affecting solar wind patterns, magnetic field configurations, and particle densities across vast volumes of the inner solar system. Ground-based observations show that the coma's expansion rate varies with the visitor's rotational period, suggesting that different regions of the nucleus contribute to atmospheric growth at different times during each rotation cycle. But the massive atmospheric expansion represents more than just scientific curiosity. Such rapid changes could fundamentally alter the visitor's response to solar heating in ways that make its future behavior completely unpredictable. Solar heating and massive outgassing could alter this visitor's trajectory enough to redirect it toward Earth, Mars, or other populated regions of the solar system, with catastrophic consequences. Spacecraft navigation relies on the principle that objects in space follow predictable trajectories determined by gravitational forces. This visitor violates that fundamental assumption through active outgassing that creates thrust forces impossible to calculate in advance. The asymmetric mass loss acts like a natural rocket engine, pushing the visitor in directions that depend on which side of the nucleus is most active at any given time. As the object rotates and different regions face the Sun, these thrust forces change both magnitude and direction unpredictably. Computer simulations show that even minor trajectory changes could have enormous consequences over interplanetary distances. A course deviation of less than 1 degree during the current solar approach could redirect the visitor toward Mars's orbital zone during the planet's next passage. The exotic chemical composition makes thrust calculations particularly challenging. Carbon dioxide outgassing creates different momentum transfer characteristics than water vapor, while the metallic components add variables that existing orbital dynamics software cannot handle accurately. The visitor's enormous coma acts as a solar sail, catching solar wind pressure across its 200,000-mile diameter. This interaction creates additional forces that compound the unpredictability of trajectory modifications caused by direct outgassing. Historical precedent shows how dangerous, unpredictable comet behavior can be. Several well-studied comets have experienced sudden trajectory changes that caught astronomers completely off guard, sometimes redirecting objects toward planetary collision courses. The timing of potential course changes coincides with the solar conjunction period when Earth-based tracking becomes impossible. Any trajectory modifications occurring behind the Sun would not be detected until the visitor emerges in December, potentially too late to calculate new impact risks. The visitor's hyperbolic velocity amplifies the consequences of even small course changes. At 61 kilometers per second, minor deflections translate into enormous positional differences over the months required for the object to traverse the inner solar system. Mars represents the most vulnerable target for potential redirection scenarios. The visitor's current trajectory passes through the red planet's orbital zone, and relatively minor course changes could time this passage to coincide with Mars's presence in the intersection region. Earth faces lower probability risks, but potentially catastrophic consequences. While major trajectory changes would be required to redirect the visitor toward our planet, the enormous kinetic energy of an interstellar impact would exceed any natural disaster in human history. Current planetary defense systems were designed to handle asteroids and comets originating within our solar system. Objects following predictable orbital patterns can be tracked and potentially deflected with years of advance warning. Interstellar visitors operating under completely different rules render existing defense strategies ineffective. The visitor's trajectory modifications could also affect its interactions with other celestial bodies. Course changes that avoid direct planetary impacts might still create close encounters that disrupt asteroid orbits or destabilize small moon systems. Multiple space agencies have begun preliminary discussions about emergency response protocols for unpredictable visitor behavior, but current technology provides limited options for tracking or intercepting objects moving at interstellar velocities. The gravitational influence of Jupiter and other gas giants could amplify small trajectory changes into major course corrections. The visitor's path carries it through regions where planetary gravity wells could redirect even minor deflections into significant orbital modifications. Amateur astronomers and international observation networks have been placed on alert to immediately report any apparent changes in the visitor's position relative to background stars, providing early warning capability for trajectory modifications. The unpredictable nature of the visitor's behavior means that impact scenarios cannot be ruled out based on current trajectory analysis alone. Continuous monitoring remains essential until the object exits the solar system entirely. But regardless of trajectory changes, the visitor must eventually emerge from its solar hiding place. When it reappears in December, we may be looking at something completely different from what disappeared in October. When this visitor emerges from behind the Sun in early December, it might be a completely transformed object, fragmented into multiple pieces, or fundamentally altered by the intense solar heating it experienced during conjunction. The solar conjunction blackout will end abruptly when the visitor reappears in Earth's dawn sky, providing astronomers with their first glimpse of an object that has undergone weeks of intense thermal stress completely unobserved. Perihelion passage represents the most traumatic experience any comet can endure. Solar radiation at the visitor's closest approach will be over 100 times more intense than anything it experienced during 7 billion years of interstellar travel, potentially triggering changes that dwarf all previous observations. The reacquisition process itself could prove challenging. Astronomers will need to relocate an object that might have changed dramatically in brightness, trajectory, or even fundamental structure during the unobserved period. Standard search procedures assume objects maintain predictable characteristics. Historical precedent shows that comets often emerge from solar conjunction completely transformed. Some objects fragment into multiple pieces, others undergo explosive brightening, and a few disappear entirely after apparently disintegrating during closest solar approach. The visitor's exotic composition makes its post-conjunction behavior impossible to predict using models developed for normal solar system comets. The dominance of carbon dioxide and trace metallic compounds could create outgassing patterns unlike anything previously observed. If fragmentation occurred during conjunction, December observations could reveal dozens or hundreds of separate objects following slightly different trajectories. Each fragment would require individual tracking and analysis, multiplying the observational challenges exponentially. Alternatively, the visitor might emerge significantly brighter than before if solar heating activated previously dormant regions of the nucleus. Explosive outgassing events during conjunction could expose fresh interior materials to solar radiation, creating dramatically increased activity levels. The possibility exists that the visitor could emerge dimmer or completely invisible if the nucleus suffered catastrophic disruption during perihelion passage. Some comets have effectively evaporated during close solar encounters, leaving behind only dispersed debris fields. Weather conditions during the December reacquisition period could further complicate observations. Northern Hemisphere winter often limits telescope operations precisely when clear skies would be most critical for relocating and studying the transformed visitor. The visitor's post-conjunction trajectory might differ significantly from pre-conjunction predictions if outgassing events during solar heating created substantial thrust forces. Astronomers could find the object in completely unexpected regions of the sky. International coordination becomes crucial during the reacquisition phase. Observatories worldwide will need to work together to quickly relocate the visitor and begin comprehensive analysis of whatever changes occurred during the hidden solar encounter. The scientific value of post-conjunction observations could exceed all previous data combined. The visitor's response to intense solar heating will reveal internal structure, composition variations, and physical processes that remained hidden during the gentler conditions of its approach phase. Emergency protocols may be needed if the visitor emerges as multiple fragments following divergent trajectories. Space traffic control systems would need rapid updates to track new debris patterns and assess collision risks for spacecraft and planetary bodies. The December emergence occurs during a period when amateur astronomers typically enjoy optimal viewing conditions. Citizen science networks could play crucial roles in early detection and preliminary characterization of the transformed visitor. Advanced instruments, like the James Webb Space Telescope and Hubble, will need immediate reconfiguration to study whatever emerges from conjunction. Observation schedules, developed months in advance, might require complete revision based on the visitor's post-conjunction characteristics. The timing of emergence could coincide with other astronomical events that limit observation capabilities. Solar activity, lunar interference, or planetary alignments might restrict the available windows for studying the visitor's transformed state. But before the visitor can emerge transformed, it must survive one final gauntlet. Its current path carries it through the most dangerous region of our solar system. The visitor must navigate through over 1 trillion rocks, larger than 60 feet across, any one of which could shatter this 7 billion-year-old relic into fragments or deflect it toward populated planetary regions. The asteroid belt represents our solar system's most hazardous navigation zone, containing debris left over from the violent process of planetary formation 4.5 billion years ago. This cosmic minefield extends from roughly Mars's orbit to Jupiter's, creating a gauntlet that tests the survival capabilities of any object passing through. Current surveys have catalogued over 1 million asteroids larger than half a mile across within the belt, but these represent only the largest and most easily detected objects. Computer models suggest the total population of potentially dangerous rocks exceeds 1 trillion individual pieces. The visitor approaches this region at hyperbolic velocities that make collision avoidance impossible through gravitational maneuvering. Unlike spacecraft that can adjust course to avoid known hazards, the visitor must maintain its trajectory regardless of obstacles in its path. The statistical probability of collision depends on the visitor's cross-sectional area and the density of asteroids along its specific trajectory. While space between asteroids appears vast, objects traveling at 61 kilometers per second encounter vastly more potential collision partners than slower-moving bodies. The visitor's expanding coma creates an effective target area much larger than its solid nucleus. The enormous atmospheric envelope, stretching over 200,000 miles across, could interact with asteroid fragments too small to threaten the nucleus directly, but capable of disrupting the outgassing processes. Impact velocities between the visitor and asteroid belt objects would reach extraordinary levels. Relative speeds could exceed 100 kilometers per second, creating collision energies that would vaporize both objects instantly, regardless of their composition or structural integrity. The exotic materials composing the visitor's nucleus might react unpredictably when subjected to high-velocity impact. 7 billion years of cosmic processing could have created crystal structures or chemical compounds that become explosively unstable when disrupted by collision shockwaves. Fragment dispersion from a major collision would create secondary hazards throughout the asteroid belt region. Pieces of the shattered visitor traveling at interstellar velocities could impact other asteroids and create cascading collision events that persist for decades. The visitor's forward-streaming particle buffer zone might provide some protection against smaller debris, but objects larger than a few meters would overwhelm any natural collision avoidance system. The ancient wanderer relies entirely on statistical luck to survive its transit. Gravitational interactions with the largest asteroids could slightly deflect the visitor's trajectory, potentially redirecting it toward more dangerous encounter scenarios with planetary bodies. Even minor course changes could have significant consequences over interplanetary distances. The asteroid belt's irregular mass distribution creates unpredictable gravitational effects that could influence both the visitor's trajectory and the orbits of nearby asteroids. Such interactions might increase collision probabilities for months after the visitor's passage. Detection of potential collision partners remains impossible using current technology. The visitor moves too rapidly for real-time tracking of smaller asteroids that could pose impact threats, leaving collision avoidance entirely to chance. The timing of asteroid belt transit coincides with increasing solar heating and accelerating outgassing activity. The visitor will be at its most unstable precisely when it faces the greatest collision hazards, compounding the risks of catastrophic disruption. Historical observations show that several comets have disappeared or fragmented while transiting the asteroid belt region. The combination of solar heating stress and collision potential creates conditions that test the structural limits of even well-preserved cometary nuclei. If the visitor survives its asteroid belt passage intact, it will emerge as one of the most durable objects ever observed in our solar system, Such survival would provide additional evidence for either extraordinary natural preservation or artificial construction designed for interstellar travel. But even successful navigation through the asteroid belt cannot prevent the inevitable. This ancient messenger is racing toward a final departure that will take all its secrets beyond human reach forever. After its brief visit to our solar system, this 7-billion-year-old wanderer will accelerate back into the void between stars, carrying away secrets that humanity may never have another chance to discover. The visitor's hyperbolic trajectory ensures that its interaction with our solar system represents a unique historical event that will never be repeated. Unlike periodic comets that return predictably, this ancient traveler is making a one-time passage through our cosmic neighborhood. Escape velocity calculations show that the visitor will reach maximum speed during its December emergence from solar conjunction, accelerating to over 70 kilometers per second as it begins its outbound journey. At such velocities, it will cross the orbit of Jupiter within months and exit the solar system entirely before the end of 2026. The final departure carries profound implications for scientific understanding. Every unanswered question about the visitor's composition, structure, origin, and purpose will remain permanently unanswered once the object disappears beyond the range of human observation and communication. Current spacecraft technology cannot intercept an object moving at such extreme velocities. Even if a mission were approved and funded immediately, no existing propulsion system could achieve the energy levels needed to match the visitor's trajectory and conduct close-range studies. The scientific data already collected represents humanity's only sample of materials from the galactic thick disk region, potentially the oldest matter ever studied directly. Future analysis of spectroscopic data and observational records could yield discoveries for decades to come. The visitor's departure will mark the end of the most intensive astronomical observation campaign in history. Telescopes worldwide have coordinated unprecedented international cooperation to study this ancient wanderer, creating collaborative frameworks that could benefit future astronomical discoveries. The final observations will focus on long-term changes in the visitor's activity levels as it moves away from solar heating. Understanding how ancient ices respond to decreasing temperatures could provide insights into preservation mechanisms operating across cosmic timescales. Radio telescopes will attempt to maintain contact with the visitor for as long as possible, searching for any electromagnetic signatures that might indicate artificial systems or unusual physical processes operating within the nucleus. The visitor's trajectory will carry it toward the constellation Lynx, in the direction of the outer spiral arms of our galaxy. Computer models suggest it will require roughly 40,000 years to reach the distance of the nearest star, assuming it maintains current velocity. Amateur astronomers worldwide plan to track the visitor's departure for as long as their instruments allow, potentially extending observations beyond the capabilities of professional observatories through distributed citizen science networks. The final months of observation will be crucial for understanding the visitor's true nature. If artificial technology remains hidden aboard this object, the departure phase might reveal operational systems that were concealed during the solar approach. International space agencies are developing protocols for maintaining visitor tracking data in permanent archives, ensuring that future generations of scientists will have access to complete observational records for continued analysis. The visitor's exit will leave behind a debris trail extending across billions of miles of interplanetary space. This material could provide ongoing opportunities for study if future spacecraft encounter fragments during routine solar system operations. Theoretical calculations suggest that similar interstellar visitors might pass through our solar system every few decades, but detecting them requires advanced survey technology and favorable geometric alignments that may not occur for years or decades. The departure also ends humanity's first extended encounter with materials from another star system, closing a chapter in astronomical history that began with the visitor's discovery in July 2025. The final acceleration phase will test the visitor's structural integrity one last time as gravitational forces from the Sun's gravity well either successfully launch the object back into interstellar space or cause final fragmentation that scatters ancient materials throughout our solar system. But regardless of how this visitor's story ends, its brief passage has already taught us disturbing truths about our place in the cosmos. The lessons from this ancient messenger reveal how vulnerable we remain to forces beyond our control or understanding. This ancient visitor has revealed humanity's cosmic vulnerability, showing us that we exist in a universe where 7 billion-year-old mysteries can appear without warning, carrying threats we cannot predict or defend against. The discovery of this interstellar wanderer demonstrates that our solar system operates as part of a much larger and more dangerous cosmic environment than previously understood. Objects from alien star systems can penetrate our defenses, approach our planets, and disappear again before we fully comprehend what we have encountered. Our planetary defense systems, designed to protect against asteroids and comets from within our solar system, prove inadequate when faced with interstellar visitors operating under completely different physical and temporal scales. 7 billion years of cosmic evolution have created materials and processes that exceed our theoretical models. The visitor's exotic chemical composition reveals that the universe contains substances and formations that challenge fundamental assumptions about planetary science. The dominance of carbon dioxide over water ice, the presence of metallic vapors, and the unprecedented particle emission patterns suggest chemistry operating under conditions we cannot replicate or fully understand. The observation challenges faced during the visitor's passage highlight critical gaps in our astronomical infrastructure. Despite possessing the most advanced telescopes in human history, we remain vulnerable to observation blackouts, weather interference, and technical failures during crucial discovery periods. International coordination proved both essential and inadequate during this cosmic encounter. While observatories worldwide cooperated to study the visitor, institutional barriers and competing priorities limited the effectiveness of collaborative research efforts when time was most critical. The alien technology hypothesis, while controversial, forces serious consideration of our assumptions about intelligence in the universe. If advanced civilizations exist and conduct surveillance missions, humanity's technological development occurs under potential observation by entities with capabilities beyond our comprehension. The dark forest implications suggest that revealing our location and capabilities through radio communications might attract attention from civilizations that view emerging species as threats to be eliminated, rather than partners for cooperation. The visitor's ancient origins from the galactic thick disk region demonstrate that materials and objects older than our solar system continue to influence cosmic evolution in ways we are only beginning to understand. The universe operates on timescales that dwarf human civilization and carry consequences across billions of years. The debris field created by the visitor's passage will affect solar system navigation for decades to come, illustrating how brief encounters with interstellar objects can create lasting consequences that persist long after the original visitor has departed. The mass loss acceleration and unpredictable trajectory changes show that even natural objects can behave in ways that exceed our ability to predict or control. The universe contains forces and processes that operate outside the boundaries of human understanding or technological capability. The toxic atmosphere and chemical contamination demonstrate that interstellar visitors can pose biological threats to life forms throughout our solar system. The cosmos contains materials and processes that could render planets uninhabitable or destroy ecosystems that took billions of years to develop. Our spacecraft and space-based infrastructure remain vulnerable to threats moving at velocities that overwhelm existing protection systems. The democratization of space access has created hundreds of potential targets for destruction by objects we cannot track or defend against. The limited observation window reveals that humanity often gets only one chance to study cosmic phenomena that could answer fundamental questions about the universe's structure and evolution. Scientific opportunities lost to weather, equipment failures, or scheduling conflicts may never return. The visitor's eventual departure will carry away more questions than answers, reminding us that the universe operates according to principles and timescales that exceed human comprehension. We remain newcomers in a cosmos filled with ancient mysteries that may be impossible to solve. This encounter has taught us that Earth exists not in isolation, but as part of a dynamic and potentially dangerous galactic community, where 7 billion-year-old visitors can arrive without warning, challenge our understanding of reality, and disappear again into the void between stars. We are not alone in the universe, and we are not safe.